All right, so in this video, we're gonna develop a linear regression model from scratch. When I mean scratch, what I mean is we will not use any libraries. Rather, we will just use raw mathematics and convert that into actual code using Python and numpy. So then we will train that algorithm which we develop on a data set. And for this project, I've chosen the California housing data set. And just to save time as well, I've also written the script for data prep and the model actual triggering of training and evaluation part. But we will actually write the script from scratch for the implementation for that's where we actually build the algorithm by converting the math we see here on the first section into actual code and how we actually set up the class. Okay, so now that's it. And just for us to quickly run through and understand how the actual model works. Okay, you need to focus on these four bullet points here. Okay, so linear regression is nothing but finding a line, okay, or creating a best line in a graph which actually makes a prediction. Okay, in simple words, as you could see on the right side, if you take this graph, right, it's a two-dimensional graph, right? We have the x-axis and the y-axis. Okay, now let's take our data set for an example. Okay, in our data set, if I go here and show you a little bit, if I run this, you see a lot of columns, right? Medium income, house age, average room, average bedrooms, population, occupation, latitude, longitude, and the median house value, which is nothing but the house price, right? So let's say let's say you work in real estate and you've been tasked to develop an algorithm, or in simple words, you've been asked to predict the price of any new house the client brings into your office starting tomorrow. Okay, the only way for you to predict new house which is not even in this data set is by trying to find and understand patterns in the data you already have, okay, which is this data set. Okay, now median house value, like I said, if you want to predict the price, this is the data we have on this data set. Okay, that is going to be our y value. Okay, and on the right side I marked that as house price y. Okay, and let's say I'm gonna see in a production in a like a very good linear regression problem, like, or even how we are going to program it, we are going to use several inputs, not only one input or one feature in machine learning terms. When I mean input of feature, what I mean is the other x value on the graph which we will use to predict the y value, which is the house price. Okay, but just for the sake of explanation, I'm going to use the median income as the house price. Okay, oh sorry, median income as the input or x feature. Okay, now let's say if I take these rows, right, from median income and median house value and I plot it. Okay, and when I plot it in the graph, let's say I just see something like this. Okay, and of course there are outliers here and there. Okay, so the entire linear regression model, or the whole purpose of training the model, is trying to find a straight line which goes through this data point. It doesn't have to touch all the data points. It just needs to fit properly or be as close to this historical data so it can make predictions on future values as accurate as possible. Okay, so let's say in this case the line actually goes like this. I'm just going to take a ruler, and I'm just going to draw a line here. Okay, let's just say this is the straight line. Okay, and just to get it out, we know the let me just try to move this a little bit so you guys can see. Yeah, so in simple mathematical terms, right, the equation of the straight line is y is equal to mx plus c. I'll explain what each of these variables stand for in a bit, but that is the simple equation or the formula for a straight line as per general mathematics and statistics. Right, now let's come back here. Now let's say this is the perfect line for this particular input feature and the y, the predicted price, right? So now if tomorrow my client comes into my office and says that he needs to predict a price of house which is in the neighborhood of medium income, whatever, let's say 4, right? I don't even have to wait for him to say what's the house price. I can just pull up this graph and I can just plot this out and find the predicted price. And this is how you do it. Let's say the house is in the area where the median income is 4, okay, or 4,000 per month, right? As you could see the unit. All I have to do is go to x-axis, find 4, and draw a straight line connecting it to the straight optimum line which we have found. And the corresponding y-axis is the predicted price. In this case, it will be somewhere around 35. Okay, that's how simple it is. Okay, the whole point of training this algorithm is finding the perfect line. Okay, when I mean perfect line, okay, just if we actually develop a model which doesn't have a perfect line, let's just say, for example, right, instead of this red line, let's just say, let me just take this, let's say the line is somewhere here. Okay, now if you have to predict, right, for the predict the price of the same house at the same neighborhood at the same cost, right, if I the predicted price will be so different because the line is in a different place, right? And this could be wrong, right? So how do we find the perfect line? And that is where we bring in the prediction equation. Okay, so we take y is equal to mx plus c, which is a standard mathematical formula for a straight line, right? So where x stands for the input, m is nothing but slope. Okay, slope is nothing but how much we can tilt the straight line. Okay, so initially we had this straight line here, then we tilted it here, right? That's the second straight line. So how much we can tilt the straight line to pack it as closest to the data points, or to pack it as close as it fits properly, right? And c is nothing but the intercept. Intercept is nothing but the point where the y-axis meets the straight line. In this dummy example I drew, it's at 0, right? So it's basically, in simple terms, we adjust intercept c to move the line up and down. Okay, where m works on tilting it, we the adjusting c will help us move the line up and down. Okay, now in machine learning terms, the same equation or the formula is also called as hypothesis function h of x. That's what you see up here. Okay, or we also denote it by y dash. Okay, so let's just say hypothesis function h of x or y dash. Okay, now the formula is exactly same. Okay, we are just replicating the same straight line equation, but in machine learning terms we have different terms. Okay, so y dash is nothing but, instead of m slope, we call it weights w. Okay, but the working process is still the same. The job of adjusting weight is to adjusting the tilt. Okay, and x is input, it stays the same, and instead of c intercept, we have b bias. Again, the meaning still remains the same for c or b. Okay, now that is our prediction equation. Okay, so every iteration, what happens is, of, let's say you have 1,000 iterations of training run, right? So every iteration it makes a prediction. Okay, then what happens once it makes a prediction on the x value, right? Then in order to understand how wrong the prediction is, in order to penalize and make it better, that's where the second point comes in, the cost function. Okay, the cost function is nothing but taking the difference between CF is equal to y dash minus y, where y dash is the predicted price and y is the actual price from the data set for that data point. Okay, and that will be a particular value. So what we do is, in order to make it, so what will happen is that this is a data point for one, this is a cost function for one data point, right? Now there could be, even this data set has 20,000 rows. Okay, now this operation will happen for all the 20,000 data points. Okay, and basically the formula you see here is nothing but, we are just taking the summation, we are just taking all these 20,000 data cost functions, okay, squaring them so that they won't cancel each other out. Then we are taking the average of it. Okay, then we try to adjust the w and the b, which is slope and the intercept, okay, or weights and biases. Okay, and the process we follow to adjust the weights and biases is nothing but what you see here. The whole point of gradient descent is to help us find the w and b that makes the cost function as small as possible. Okay, so, and that is where we use chain rule to find the derivatives. Okay, and once we do that, we basically then find the learning rate. Okay, sorry, the update parameters. Okay, or the update rule, taking the step. So basically update rule is nothing but this actual step we need to take, okay, using the learning rate we have here. Okay, now when it comes to learning rate, if you actually give a very large learning rate, okay, it overshoots the error. Okay, and if you actually give a very small learning rate, then the training process takes a ton of time. Okay, so it is always good to start with some kind of an optimal learning rate. Usually it will be around 0.01. So that's where I used to start my linear regression training, or the learning rate, the initial learning rate I said, and that is the most common value as well, and that's what we will do here too. Okay, and that's it. Now we can jump right into the programming part of it. Okay, so let me just run you through quickly on this, what we are doing here in terms of data prep. Okay, so we are just loading the data set here from scikit-learn data sets. Okay, then we are doing small EDA. If I run this, you will see we have 20,640 rows, okay, of values of data. Okay, and this is the distribution we have of median house value, which is the feature we are going to take. Oh, sorry, which is the target price, right? I mean the target factor, right? Or the price we are trying to, or the value we are trying to predict. Okay, then we need to plot the distributions of the features to understand. So then we have to do something called normalization. Okay, so the reason we do normalization is pretty straightforward. Okay, for example, let me just show you this. Okay, let me just run this. Okay, so as you could see now, it shows an histogram, like multiple histogram of the distribution of other columns or data points we have, right? So if you take the uh, population, okay, so now the population, it ranges from, let's say, thousands, right? I guess, as you could see here, let me just try to zoom in a little bit. Yep, ranges in the thousands. Okay, where median income, if you take median income here, it ranges in the 0 to 15. Okay, as you can see the difference here. Okay, now if we train the model as it is, if we feed in this data as it is, what will happen is basically the gradient for population will dominate and the gradient descent will fail. Okay, because in general the populations have higher value range, right? So that will make the gradient descent to fail. So what we are trying to do is we are just trying to normalize it. Okay, so we use basically z-score here, which we have written here. Okay, then once we hit that, we will get the data as normalized. Okay, and we are ready to go to the start writing the fun part, which is actually writing or converting or implementing the model from scratch, which means we are just going to convert all these mathematical equations, okay, into code. Okay, and this is just a small explanation of what we're doing. The hypothesis function, okay, is that basically this prediction equation you see here, y dash wx plus b. Then the cost function evaluate how wrong we are. The gradient descent is basically helping us find the optimal w and b to minimize the cost as much as possible. Now, all right, so this is what we are gonna do. Okay, so I am gonna first create a class. Okay, I'm gonna name the class linear regression. Okay, and under this class is where we will develop, write multiple functions which will each do one task. Okay, we will write a function for the prediction equation y dash is equal to wx plus b. Then we'll create a function for the actual learning mechanism. Okay, then we will create a function for predicting. Okay, then we will create a function for computing the cost. Okay, so before that we need to set up, right? So let me see, let me write. So let's set up the rules first. Set up the ground rules. Okay, now this is where you say def, and I could see the auto code editor, I mean Google Colab's auto generator is generating the codes for me here, and it's looking exactly what I want, so I'm gonna accept it. Okay, so what's happening here is that you're initiating the function. Okay, and you're setting the learning rate, the alpha, to 0.01, and the number of iterations, which is the number of training runs, to 1000. Okay, then we are setting learning rate to learning rate, number of iterations to number of iterations. Then we have self.weights. Like I said, when we initially start training the model, the weights and biases will be random. Okay, so first just set it as blank for now. Okay, then self dot bias is equal to none. Okay, then I will write this so that we can capture the cost changes and plot the cost curve. Okay, so history. All right, so let me remove this. Now that's the initial setup. Okay, now let me first write the function, okay, for, let's say, what will happen, okay, or how do we predict. Okay, at any point, if we ask the model to predict, we want the model to make the predictions with the current or latest weights and bias, right? So what we will do is we'll do definite function predict self comma x comma, that's it. Then we will do return np dot x self dot weight self dot bias, which is nothing but the prediction equation. which we saw on the right side. Okay, now let's also write the compute cost function. It's of x comma y, sorry, y. We have to do n samples, is the number of training samples we have, is x dot shape 0. Then we do y predicted. Okay, so let me just write this. Y predicted is equals to self dot predicted. Is that right? Self dot predict ex cost is equal to half sample. Yep. So the auto generated, it generated correctly. Okay, so basically this is a cost function we see up here. Okay, and now we will write the actual learning mechanism as well. The actual learning mechanism. Okay, fit. Okay, and let's do self x comma y. We're just trying to bring in the number of samples, number of features is equal to x dot shape. It did generate correctly. X dot shape self dot weights. We need the weights to start at 0, so it's equal to numpy zeros and features of a bias. All right, see, we almost got it. The auto generation is pretty on point here, in which it's actually generating the right code. Okay, so self dot bias. Then what we will do for I in range, self dot number of iterations, we wanted to predict y underscore predict self dot predict x. Then we will find the gradient descent functions, which is what is happening here. Gradient descent calculations. Okay, so the first one is for, we are calculating the weights, and this is the bias. We are just basically converting all these mathematical equations into this. Oops. Then we have to update the parameters, right? So update parameters. So what we are doing is we are just right now going to convert this form, write this formula in code. Okay. So let's see, self dot weights. It's weights is equal to self dot running rate done. Yep, the autogen is again correct, so I'm just going to accept it. Okay, then we are going to calculate the cost, self dot compute, self dot compute cost for x and y. Then we are going to store the computed cost into that list which we created up here. Okay, so that's pretty much that. Now all we have to do is we have to initialize is linear regression, and print model cell or model initiated successfully. Okay, so basically what we have done here is just to run through once again. There's a space. Okay, so we have just first set up the ground rules, which is basically we have set the learning rate, the iterations, and we have assigned them properly. Then we have initially we have set that the weights and bias to none. Okay, then we also created a cost a list, cost underscore history, to store the cost errors, right? Then error head. Okay, then we created a function to make the actual prediction. Okay, at any time, let me just add a note here. Anytime, make the prediction only using the latest or latest W and B. Okay, then we basically wrote our prediction equation formula there. Then we basically calculated the mean square error here, calculating the cost values basically. Then we actually wrote the training mechanism, which is nothing but the gradient descent, right? So understanding how to adjust our W and B, and feeding the new W and B into a learning rate, and keep doing it until the number of iterations reaches. Okay, now there are several other things you can do as well. Now this algorithm will run until this 1000 iterations gets over. Okay, now there are optimization which we can do, in which you can stop the training algorithm or the training iteration as soon as the model reaches a point above which it doesn't learn well. Okay, which I will explain later. Okay, now let's just run this again. Now let's go up to the training, in which I've already written the script like I told you. Okay, so basically what we're trying to do is we are just initiating the training here, model.fit x underscore train underscore norm y underscore train. Okay, then we are computing the cost, as you could see here, using this function, compute cost function. And let's see what happens. Looks like there is a small error somewhere, as I know your shape. Where did I make that mistake? I think here. Okay, now let's do it. All right, so as you can see, the training was pretty fast, right? So it says the r square is 0.57. Okay, so because this is how I wanted to interpret r square. Okay, basically if the r square is greater than 0.7, I want it to be great fit. If it's somewhere between that, I mean, it's going to be a moderate fit. That's where the model is currently. Now there are a lot of opportunities for us to further improve this model. Let's also visualize this and see, okay, the loss curve and the actual predictions and the residual part. Okay, so as you can see, the loss curve, right? So I want you to take a look at the shape of this curve. Okay, it drops steeply, then just flattens. Okay, so the graph you see there, that is a good graph. It drops steeply, then flattens. Okay, now when it could be a bad sign is if it stays flat. Okay, that means the learning rate is too small. Okay, or bounces up. Okay, in that case the learning rate is too large. Okay, that's where you need to make tweaks as well. The second graph is nothing but the straight, and the red dot is the perfect prediction we have right now, which gives us an accuracy of r square value of 0.57 at this point. Okay, and it is mapped in terms of the x-axis is, like I said, the actual price, and the y-axis is the predicted price. Okay, so the last plot is the residual plot. Okay, so the residual plot is nothing but it's like a health checkup for your, let's say, linear regression model. Okay, well, for example, your accuracy score tells us how much you got, like our accuracy score, like r square tells you how much you got it right, how much predictions you got it right. The residual plots tells you exactly what went wrong, what you got wrong, and if your model is biased. Okay, that's pretty much what it does here. Okay, as a developer, basically the residual graph is one of the, let's say, most important graph, right? The diagonal line, see that straight orange line sloping downward on the right, that is the mathematical echo of the 5.0 price gap. So basically if you see this data set, I mean graph here, okay, in this data set, any house value above the value of 500k are capped at 500k. Okay, so if it's 600k, it is still capped at 500k. Okay, so let's see whether if we could figure something out here. Yeah, so as you can see here too in this histogram, right? So that is what the steep red line, I mean green and orange line mean here. Okay, so it's basically because of the price cap. Okay, so if you could notice here, the cloud is tight on the left, right, but gets wider as it goes horizontally or towards the right. Okay, this means your model is more accurate for cheaper houses, okay, than it's for more expensive one, which you could see on this side of the graph too. As you could see, it's more tightly packed within 0 to 4 than as it goes a little away as it comes to 4 to 5, right? So that's basically the residual plot is nothing but the plot of errors. It will show us what is the error difference, as you could see, actual minus predicted. Okay, now just to sum it up, right? So we basically wrote the prediction problem, then we actually found the cost function. Okay, then we spoke about gradient descent and learning rate update parameters. Okay, so like I said, some of the other, to make it, take it to another level or take it to the next steps, what you can do is you can basically implement early stopping, and something else you can do is also use mini batch gradient descent instead of computing gradients over all 20,000 samples at once, or like 16,000 training samples at once, right? And one reason you want to do that is because now this is a small data set, right? 20,000 samples. What if you have 200 million samples, right? Now that will, if you do gradient descent for all of this at once, it'll basically clog your computer's memory. Okay, so instead of doing that, instead of looking all the data at once, you're just taking one piece of data, okay, as a chunk, like maybe 32 or 64 rows, then keep doing it one after the other. Okay, so that's pretty much all for this video. I will see you on the next.